to look at the synergy of this AI for AI and metaphotonics. So what I want to try to show is how AI can be used for metaphotonics. So in terms of design and forward modeling and this kind of things, as well as total systems using AI inside this kind of nanophotonics and metamaterial, metasurface based optical devices, as well as using metaphotonics for AI. So that's kind of the next stage that I hope to go towards, is using these optical components and this kind of metaphotonics or nanophotonics and metasurfaces for doing AI. So this means kind of optical computing and computing using light rather than using electrons. So we want to try to move to the photon to be the information carrier and the guide to do some calculations. And so that's kind of where I try to move with my research directions as I pass through the PhD course. And so hopefully this presentation makes sense and this talk makes sense. So I'm gonna try to show you some examples of the things that we can do using AI for metaphotonics, as well as metaphotonics for AI in the current kind of state of the art, and so hopefully can get some kind of ideas and make some interesting new directions for research. So I'm going to start with some quick background about just meta surfaces and metamaterials. So I guess everyone is in this field, so I guess I don't need to spend too long. And just we know that the meta of metamaterials, this is some Greek word that means beyond. And so we can control waves, and we can control light, as well as sound waves or whatever other waves beyond what is available in nature. And so that means we can use this for visible light, for infrared light, for seismic waves. So this could be for earthquakes, for example, as well as acoustics or sound waves. So actually any type of waves can be manipulated using these metamaterials. And so the idea of this is that in natural in kind of natural materials, we can only find in this epsilon negative or mu negative, double positive, these three quadrants. But using metamaterials, we can see that actually the refractive index, when we take the square root here of this epsilon mu, one of the solutions is also -1. This is a possible solution. But the only problem is then we have to be able to manipulate the permittivity and permeability of light or whatever waves we want to use, and simultaneously to be both negative. And so this is kind of giving us light to this kind of negative refraction. And so we can imagine it's kind of the one of the first goals, or the first big potentials of metamaterials is to realize this kind of invisibility cloaking. So if we can bend the light in the negative direction, and we can guide the light to come around some people or some kind of objects, and then that allows us then to transfer the light from behind to become in front, and then we can be invisible. And so still there's ongoing research for this, but there are a lot of steps that need to be fulfilled before we can make this this Harry Potter to be some kind of realistic cloak. So for now, we are using meta surfaces. So metamaterials are quite difficult in this 3D structures. So what we do is we move to this meta surfaces, where we have this kind of a 2D shape, where we have like a quasi 2D, so 2.5D, where we have a very small height, and we can design these guys in the unit, in some unit cell, to have some different design parameters, or different parameters depending on the lengths or the materials of these guys. And we can then use this to control the wavefront of light at the nanoscale. For in terms of visible light, this should be nanoscale. But the point is that for metasurfaces, these guys should be smaller than the wavelength of light. So we can see that when the wavelength of light is then bigger than these nanostructures, or these structures, these sub-wavelength structures, then we are able to manipulate light, the wavefront, the phase, the amplitude, the polarization, and any component of light that we want, we can control in the sub-wavelength scale. And so this kind of one of the papers that kicked off this kind of meta surfaces, so to introduce this generalized Snell's law. So we have the general Snell's law that we all know from our basic optics class, and then if we then add in this extra term, so this kind of extra amount of a phase gradient, we can then say that we can then we're able to then just completely control the direction or the refraction of light as we want. And so the important part is to be able to physically encode this kind of a phase gradient, or physically encode something to control the wavefront of light in this sub-wavelength scale. And so metasurfaces or metasurfaces have found lots of applications up to now. And so this kind of when we have these optics and we have these applications, and they're known as photonics. And so I saw these days this kind of a new field is start to arrive of this metaphotonics. So using meta surfaces or meta materials for doing photonics. So this is been termed recently, this metaphotonics. So I quite like this term, so I try to use it. So this is the idea of metaphotonics. And so we have all of these applications where we put the light, and we can just control these unit cells, and we're able then to create this. So for example, meta lenses, or some sensors, or some holography, as well as recently we can also look at controlling quantum light using these meta surfaces. So there's lots of potential applications, and so this is just kind of a few of my personal research that I've done. But there are lots and lots of different applications. So anything that we need to use light, we can control it using meta surfaces or meta materials. We can think of some new applications. And so the progression of meta surfaces has been that we started off with this kind of passive meta surfaces where the structures are going to be fixed, and then so after we design this and we fabricate, and we get this this passive structure that is fixed. It has optical properties that are fixed. But as we kind of moved on, we moved on through the years, it starts to become this kind of active nanophotonics, or these active meta surfaces. So for example, here the beam steering is allowed by these interconnectors of this ITU layer, enabling us to change the optical properties using electricity. And so we start to move to this kind of a more active and more reconfigurable meta surfaces, which is much more interesting, right? Because now, for example, instead of having just a passive device, now we can use electricity, or we can use heat, or whatever stimulus we want to then modulate the optical properties of the meta surface. And then the next stage, which is being undertaken recently, is this kind of reactive, or kind of this kind of active, but including some sensing. So what I mean is these meta surfaces in this work here, for example, it it has a completely reconfigurable meta surface that we take some input sensor and then doing some calculation on the meta surface and changing the arrangement of the phase or the amplitude at the same time to then create the new optical property of this meta surface in real time, depending on the direction or depending on what is being sensed. And so I guess this is kind of the coming towards this complete complete Harry Potter invisibility cloaks, right? So now, if we can sense as well as reconfigure these meta surfaces, we will be able to improve this. But there becomes some block, especially in visible light. And here is in microwaves. So we have the unit cell is around centimeters. We can see here some 240 centimeters. It's much bigger, so it's easy enough to calculate, easy enough to experiment. If we want to use visible light, this should be in the nanoscale, so it becomes much more difficult. So this is an interesting topic, but very difficult to come to visible light. And so at the same time, I want to show that AI has also had very similar growth and very similar kind of boom. That in around 2014, we had this generative adversarial networks that use just some noise to generate and to make up some new data, and then by doing some kind of a zero-sum game, then the detective tries to choose, is this data real or made up? And so by this kind of interaction, this generator is able to generate better images to try to deceive the detector, and the detector also improves at learning what is a real and what is a fake image. And so this was kind of the start, some starting of this generative AI. And then in 2017, we had this new idea of a transformer network. So this again developed even more for what is possible in AI. And then as one of the very famous examples, we saw AlphaZero in 2018 was able to learn how to play chess, this shogi and go, and beat this very the top of the best of the best human players by self-learning and playing against himself to improve and to learn the rules and everything by himself. So this is a very interesting step for AI. And then we can see recently we have this new era of these large language models, where we have this, for example, ChatGPT, where we can type anything, or we can give any kind of an image or use our voice, and we can get some text, or we can get this to be a voice, or it's very interesting. And so we can see that AI also is getting more and more improved as time goes on. And so this kind of have a very nice synergy that improvements in AI also can be tried to be applied into this meta surfaces and metaphotonics, this field. And so to move on to AI uses in metaphotonics, I try to split this into three main topics. So forward modeling in inverse design, as well as this integrated systems. So in terms of forward modeling, the idea is then, instead of using simulators to simulate the optical properties of these structures, we can train some neural networks to then very quickly give us the optical properties. And so this kind of the main idea of this forward modeling. And so before I talk about the metaphotonics, first I want to just tell quickly a quick overview about just AI in general. So it's always confusing that we talk about AI, but we're probably talking about deep learning, and we're probably talking about generative AI if we're talking about inverse design. So inverse design is kind of in here, and deep learning is kind of in this forward modeling. So we are talking about this whole branch of artificial intelligence that encompasses many things. And so when we talk about AI, we're talking about all of these things together. So including deep learning and algorithms and all sorts of different things. So I just kind of want to clear up this part. And so what this deep learning and deep neural networks are very good at is to what we do is we can train these guys using lots of labeled data. So we get lots of data that has some specific label or something that is known, and then these neural networks are able to update their parameters for each of these neurons, and then we're able to infer what is a new thing that this guy never saw before. And so based on what it learns through these different pictures, we can then infer some new kind of the new picture. We can define what it is, for example. And so these guys are very good at learning and finding the relationships, so some quite deep and complex relationships between, for example, images and classifications or labels. So this is very interesting for us in terms of designing and forward modeling, because this looks very similar to what we want, right? We have some design, and we want to go forward, and we want to find some optical properties. And so if we can train this model to be very good at transferring between these two domains, we can then use a very fast and efficient way to kind of simulate, but without simulation, right? We're using AI instead. And so generally, when we design some meta surface, we use this kind of unit cell approach, right? So we select some geometry, we select some materials, and then we try to simulate using some simulation tools, so FDTD, FEM, RCDA, for example. And then we have to sweep, right? So we try to find, for example, we want to find the meta atom that has a very high conversion efficiency for blue light. And so then we define some parameters, and we try to sweep. So for example, if we take some simple circle, and then we wanna just take these three parameters, so this radius, the height, and the periodicity, and we want to sweep with quite generous, so just like 10 nanometers in different size in the height and the periodicity, and some 0.05 times the periodicity for the radius. And so if we do this, we take some general numbers, and so not too big, not too high resolution, just kind of reasonable. We end up with this like 21, 19, and 31 steps. So when we if we want to sweep and we want to check all of these guys together, we have to see the combination of each of these three. And so what happens is then finally we end up having to perform over 12,000 simulations. And so if we said that each simulation, for example, takes 10 seconds, and then this is going to take 100,000 seconds, this becomes hours. And so we can see that there's some need here to eliminate this part. So how can we simulate faster but keeping the accuracy, but simulate faster? It's kind of one of the big goals, right? So here's some work that has achieved this. So in this work here, they use some core shell structures, and so by learning the relationship between these three different thicknesses of this shell and using some deep neural network, they were able to then find the output scattering spectrum of this guy based on just the input here. So this is saving us the time to simulate one by one by one. And so we can see that over some kind of approximate data, we can see that the simulation, so checking the real simulation compared to this this approximation from the neural network that has learned some kind of encoding between these two, is matching very well to see the blue and the green the orange lines here overlapping very well, and we can see that they're following the peaks as well as following the dips very closely. And so in the training data, we can see that these guys are the kind of the closest guys and the far guys to the training data. So it means that this shape or this combination of thicknesses was not in the training data. So that means something was learned by this neural network to infer the new the optical properties of the new nanoparticle that is never seen before. And so we can see that the speed becomes very much faster using the neural network. So this is going to save us a lot of time and a lot of energy in terms of simulation. And then also, instead of this kind of 1D where we have just a thickness of 3 different layers, we can also use this for 2D geometry. So using the ideas of convolutional neural networks, we can then see that even though these guys are some kind of a 2D structure, we can learn the absorption spectrum, for example. So here the deep learning model is matching very closely to the real simulated response in terms of the absorption. And so with all of these random structures, even though this is completely random structures, the deep learning model, the neural network, is able to understand which parts are important and which parts give some absorption in certain wavelengths. And so it's able to gain some knowledge about this optical system by just lots of data, so lots of geometries as well as the absorption spectra. And so by learning this, we can put any random structure in here in 2D, and we are able to recover the absorption spectrum using deep learning. And so we can see that the difference in the speed is in like 60 seconds, for example. So here is around 1 minute, whereas in the deep learning here is what, 120 milliseconds. So it's a very different order of magnitude. And so, as we said, if we are going to take like 100,000 or 12,000 simulations, if we can save an order of magnitude of time, then it's very nice for us, right? And so this doesn't have to stop in 2D. This also being shown in 3D. So using nanostructure, the models in 3D or in 2D, and then to find the optical properties at every single point in the 3D space of some nanopillar. And so what's interesting here is then, if we know the electric field at every single point here, we are basically doing the same job as what we are doing when we use FDTD. So if we are able then to replace FDTD simulations with deep neural networks, it's going to be much more efficient. And then, as we know, if we have the information of the electric field and magnetic field inside any place, we can then infer and we can calculate the optical properties in terms of scattering or reflection or transmission or polarization, whatever we want. We can then very quickly get these 3D simulations. And so we can see that this forward modeling has a lot of interesting uses in terms of raw speed, to just change from having to simulate one by one. We can then use these neural networks to simulate almost instantly. And so, of course, this is very nice, but there must be some challenges, right? So we cannot just talk about the good things about this. So one of the big challenges, one of the most important parts is that here this is data driven. So that means we can see here that there's a little loss of accuracy, right? So if we look here, that there's a little difference between the deep learning model as well as the simulated model. So in terms of this, it depends on how accurate we need to be, or how important the accuracy is. Sometimes this tiny change in absorption here may be not important, but sometimes maybe it's very, very important. So for example, if our absorption peak is missed by a few tens or 50 nanometers, it could be a completely different things. And so another thing is that this guy has become some kind of black box. So inside this neural network, something is learned, but we don't know what. And so the other thing is that we have to simulate this data in order to train this guy. We need to simulate thousands of data. So is there a big difference between just sweeping or simulating the data to train? And then kind of when we come to large size metasurfaces, then we cannot forward model this guy. So we're stuck with this unit cell. So is there some way that we improve this large size metasurface simulation? And then finally, maybe there's some way to add some physics inside these simulators. But then when we start to add physics into the loss functions or the neural networks, we just start to become just a model again. It just finally we will become just to Maxwell's equations, which is exactly what we are doing in the simulator. So maybe it kind of loses the point, right? So but a very interesting things to think about. And so next, for inverse design. So rather than modeling forward, we want to take some optical response, and we want to find the design of the structure to get this response. And so for in 2018, this work showed using GAN. I always want to say gallium nitride, but here is a generative adversarial network. And so as we say before, we have a generator that tries to fool the critic. And so this guy tries to fool the critic. And then when this is well trained, we can then create some structures that give us some desired optical properties. So for example, here we wanna find this dip here, and then the generator is able to very easily design this kind of meta atom here that we cannot use by just our brain, right? We could never come up with this kind of a blob kind of structure. So this gives us a kind of new degrees of freedom and ideas of how to create these resonances that we want. It would be very interesting if the inverse design then gave us some new kind of a physics that we could try to understand, but until now that's kind of a bit lacking. And then in this work here, this is something that I did, was using reinforcement learning. So in this case, rather than training with labeled data, what we do is we get some state. So we define the thicknesses of these guys, and then the neural network is designed to choose an action. So the action is maybe to increase the periodicity or to increase the height. And so the agent is then choosing some action and then get some reward. So this is kind of similar to how people learn. We do something, we touch some fire, it's hot, we get burned, we know again later there's fire, we don't touch it. So we kind of learn through this kind of a process of, in this situation, what is the good action to take? And so what I show in here was then in this state here where we have a potential over 1 billion different structures in just like 100 or 200 steps. I train this model based on Chromium, and then in around 100 or 200 steps is able to optimize some ultra broadband absorbers for all of these different kind of metals. And so this is very interesting to train just one time and moving to lots of different different materials. Next, this one, we use this gradient descent. So what we do here was we create the whole framework here. So we use a scalar diffraction to come from the phase profile to give some hologram at some specific location in space. And so we create this kind of these Fresnel holograms, and then because we use here we write this scalar diffraction using PyTorch, and so that gives us the access to this automatic differentiation. And so what happens then is we can take the whole phase profile at once. We can use our scalar diffraction to propagate to different locations in space, and then we can get some loss function that compares the light intensity compared to the image that we want, and then we can use automatic differentiation to then update every single pixel at the same time. And so in this work here, we use this in around 200 iterations. So this guy goes around 200 times, and we're able to then create this three location holograms, as well as this 18 depths kind of a 3D holograms. And so another very interesting method is this topology optimization. And so this starts in the macro scale, and we move to the nanophotonics. So what we do is we have to use just two simulations. So we do a forward simulation and a joint or backward simulation. And then from these two guys, we are able to find some gradient. And then again, we do a very similar thing, that we are able to update the entire structure in one pass of these two simulations. And so what this gives us is this very random or kind of unintuitive structures. And so here in this work recently in Science Advances, they were able to create this multi-layer 3D printed metal lenses that use this topology optimization to change the size of the structures inside each layer of this metal lens. And so this creates some achromatic metal lens. And so again, the challenges and the problems of this inverse design, we have this kind of black box nature. So we do a lot of simulations. For example, here we do a lot of simulations, but it's just kind of wasted and disappears. Another thing is that we cannot be sure that we find this global optimum. So we try to optimize, or we try to find a good solution, but we just find a good solution, maybe not the best. And then finally, when we have this coupling, or when this guy is making some kind of a structure, we have to be sure that we can make it in real life for it to be useful. So there's lots of interesting also problems with this kind of inverse design.